Okay. So, the previous lecture, we concluded that if we shine an X-ray wave into a lattice, we can get reflection in very specific directions. And we wrote down the von Laue condition. Amazingly, yes. It's even on tape if there is. And we have shown that this condition is basically the same as the condition, the Bragg condition for scattering. This, to my taste, is nicer, easier, just a combination of vectors. Now, let's assume that I want to do an experiment. Okay, sounds no problem. Choose the incoming K, put your detector at the outgoing K, verify that it follows this condition, and all is well. You'll see there a peak. Doesn't fulfill the condition, you'll see there nothing. Okay, unfortunately, that's a great idea when you're working on a lattice that you know its structure, meaning you know. Okay, but if you are investigating a new lattice, this is painful. Why? I need actually 3 volunteers here. Please, 3. חניך תורן שאני אמנה פה. Under no numerical convention, 1 is 3. Okay, another one. And another one. Come on. 5. These look innocent, but they're heavy. So if you want to back down, he will replace it with. Okay, let's assume that this is my sample, and I want to send a wave in this direction. Please hold it. It's heavy. Okay, it's coming in. This is K. Another volunteer. Now I'm putting my detector somewhere here, and I want to ask, will I see any signal in that direction? Let's assume that this is large K. What is the condition? Okay, you can hold it. You have to, this plus this will be equal to this. You see how much fine fiddling you have to do in order to get a result. And no one assures you that this is the K of the sample you have. Okay, I'll stop for a minute. You don't have to freeze here.
זה חוץ זה מדע ככה
Okay. So basically, I think you got the point and you got your exercise for today. People tend to ignore the fact that metals are really heavy. Okay, so our problem is, well, not so much our problem. Experimentalists that want to measure the reflection from a lattice have the problem of they basically have to go through all kinds of angles, a lot of angles, sweep their detector, and try to find out if they see a signal or don't see a signal. Of course, nowadays you can put a robot that will move the detector and just sweep through the whole phase space, the whole possible angles. Can be done. In the 1910s and 1920s, when a lot of those experiments were performed, that would have taken a huge amount of time just to do it. These detectors are heavy, it's not something you move by hand. And and you can put perhaps the detectors and move the sample. That's a method that we'll talk in a moment. But people were looking for better ways to find out where are these constructive interference, where we get these Bragg peaks of the X-ray. So let's start just from looking at a two-dimensional lattice and try to get some intuition about this problem. All I'm talking about in the first half of this lecture is the second half of chapter 6 in Ashgrove, which last time we had reached more or less the half of this chapter. Okay, so let's assume I have, okay, this is a reciprocal lattice. Someone can tell me of what kind of real space lattice it is?
SC.
SC, not a simple cubic, two-dimensional simple cubic. Yes, the distances here will be 2 pi over 8. Why do I draw that? Because it's the simplest. Let's assume my X-ray source gives me some wavelength lambda. Which has a normalized length of 2 pi over lambda. So I'm drawing it and I put my source in some direction compared to the lattice. What do I know? If I'll take some direction k prime and try to look whether I have a point, whether I see some reflections there. Most probably I will not see anything, because in order that this minus this will be equal to the reciprocal lattice vector, it has to be on some point of these black points. Actually, whatever direction K prime takes, let's assume that it's a circle. So if the circle where this is the center of the circle and I'm sweeping K prime in all directions, if I go through a point, yes, I'll have a point. If I don't go through a point, tough luck, I won't see anything. So I have to be lucky twice. I have to have the correct length, and I have to have the correct wave function. Oh, sorry, wavelength. Because if, let's say, it's a bit bigger, no matter what direction I'll choose, I'll never see anything. And not seeing nothing doesn't prove that I don't have a lattice or I don't have a reflection. Could have many reflection points. Nevertheless, I won't see it. Okay. Center. I take it from some lattice point. Is it important which lattice point I choose? No, because all lattice points are the same. That's the definition of a lattice. I draw K, the blue vector, just according to the length, the wavelength and the direction. And then I emulate the position of the detector by taking K prime and sweeping around in a circle. That gives you all the possible directions of K prime. Okay. By the way, here you have the answer why I have to use X-rays. No. Let's replay. More exercise. I come in with a certain wavelength and a certain direction. That's K. K is a blue K. K is fixed. I don't play with it. Moving your X-ray machine is not easy. Well, at least even when you're at the dentist, you see a whole structure that he has to move around. So you fix it at some direction, and let's say put your detector. So your detector, you know that K prime, the length of K prime is defined again by lambda. So you have no freedom playing with that. So what's the only freedom you have? Moving your detector around. This is the circle, and if it would have been a three-dimensional picture, it would be moving a sphere. Unfortunately, I'm not good at drawing three dimensions, so you'll have to imagine according to the two-dimensional case. Yeah?
Why we shouldn't have a place of the detector that the circle is bigger and then the dot is immediately, for sure it is...
Okay. Hold the thought in a moment. I want to ask you a different question. Please explain me why I have to use X-rays.
They have a smaller wavelength.
Exactly. Pay attention. This guy, this length, is 2 pi over A. A, as we have seen in the previous lecture, is about between a couple to 5-6 angstroms in all typical lattices that exist in nature. Therefore, if I'll have a much larger wavelength, everything happens in something of the order of, and I'm drawing it here, something like that, right? Larger lambda, smaller vector. Here, whatever you'll do, you'll never fulfill this condition. So in order to see some reflection from a lattice, you have to have a wavelength which is orders of a few angstrom, meaning X-rays. So, how can you improve your chances of seeing something in the measurement? One of the oldest tricks in the game, it's known as Lauer's method. Once you vary lambda, you don't keep a monochromatic, well, you should keep a monochromatic, but your source gives out different wavelengths and you each time filter out and leave only one wavelength and then measure, go through different wavelengths, your chances of hitting a point increases. Because then you're sampling a lot of more of the phase space, of the lattice space. And that's known as this guy, as well as Bragg, got a Nobel on understanding how to do crystallography with X-ray, and actually, it's worth mentioning that this guy was the only member of the Prussian Institute Academy of Science that didn't vote for throwing out Einstein out of the academy when the Nazis came into power in Germany. So, more or less sad thing, but only one person there had enough of a backbone to stand up and say, "Are you crazy? You're throwing out Einstein from the academy?" Okay, second method. Well, it's almost trivial. Basically, it tells you don't go around with a large detector and move it around your lab. Move your sample. Same as doing this red circle, but much easier mechanically, less time consuming. What is powdered crystals? In the first lecture you had this tube with very small crystals in it. So instead of putting one monolithically big crystal into your measuring device, put a lot of small crystals, which each of them is oriented in some direction. And by chance, you'll probably hit a few which have the right K direction to give you reflection. Basically, if I'll draw actually, I don't want to draw it here. At least they did some treatment to the blackboard, and now it seems to be a bit better. Okay, so here is a reciprocal vector, K, for a given crystal. What happens if I have a lot of small crystals in all directions? The length of this vector doesn't change, but its orientation changes. So how do I represent it? A circle in 2 dimensions, a sphere in 3 dimensions. I come with my beloved K and shine it at some direction. Take K prime, and if I'm not on this specific K, there are a few K's, remember. I don't get. But then I can also move K prime, move my detector. Let's move in the detector. Here I have much more probability of hitting some point with reflection. No. This guy is the possible case. Now I'm rotating K. The blue K is still at a given direction. And K prime, now I'm changing only the angle of the detector. I'm changing the angle. And all I have to do is K minus K prime, or K prime minus K is equal to large K. Very annoying, this large K. A lot of textbooks use large G, and then you are not disturbed by small K's and large K's and getting confused between them. But unfortunately, I'm not so sure why Ashcroft chose large K, and I'm sticking with his representation. Okay, so still here about how do I measure these reflections. Okay, we have actually 3 additional questions about measuring X-rays, X-ray diffractions. One, what happens if I'm on a non-Bravais lattice, meaning a lattice that has a Bravais structure but still has more than one atom at a given lattice unit? Then I'll have additional scattering points. So that's the first question. The second question is, atoms are not point objects. We're talking already on wavelengths that the length is a few angstrom. An atom is, the size is comparable, half an angstrom to 2-3 angstroms. So the fact is that the electromagnetic wave is not scattered by something that could be thought of as a point. It's more scattered by some fuzzy ball of charge around the atom. So how do we take that into account? Third point is, maybe some of you have noticed, we live usually at a temperature of around 300 Kelvin, not 0 Kelvin. What does it mean?
Random noise from the atoms?
Atoms move. They have kinetic energy and they move out of their lattice points. It's a perfect lattice only at 0, the absolute 0. So, well, you can go to your lab and try to reduce the temperature to get a better picture, but still, you have motion. But motion won't be just random as in a gas. You have here still a lattice structure. So the first 2 questions we'll answer immediately. The third question moves us into a different subject, which is what vibrations do we have in lattices? This is important both for X-ray scattering, but even more so for electrical properties of metals and semiconductors, because the main scattering mechanisms at room temperature are these lattice vibrations, the fact that the atoms don't sit at one point. Okay, so after we finish answering the first 2 points, we'll move to basically, until now, we had a heuristic model. We have a lattice, what will be the properties? Now we have to answer the question, why do we have a lattice? Well, I'll start immediately. What happens when I'm not in a Bravais lattice, but a Bravais lattice that has more than one atom for each lattice unit, which is very common.
The X-ray can hit either atom.
Excuse me?
The X-ray can hit either atom.
Exactly. Here I took, it hits the point of the Bravais lattice.
Yes, but if it can't.
So, lovely. If I'm careful enough, I can build a Bravais lattice that each time sits at least on one, not at least, sits on one of the atoms of the underlying structure. But what happens to the other lattices? They take part in scattering. They're physical objects. They don't care that decided to bunch them up in this way or another way into a Bravais lattice. Some improvement, but not really. Okay. So let's assume that we have let's write it this way. Atoms at position So, for example, and so on and so forth. I have one additional atom. I could have 17, then I would draw 17 additional points around the Bravais point. So I have in each unit cell 2 atoms here. So let's remind ourselves what was the conditions that we started the game with. What was the condition?
Came in escape prime equals Q.
And why was that?
In order for X-ray to come through the lattice.
In order to have
Friction.
the interference should be 2 pi to get a phase 2 pi between them, right? Our condition was actually right? One, sorry. Okay. So now, what is the condition in order to get constructive interference. Okay, of course, that forces me. This would be 2 pi m. And from there we got this connection that this is the reciprocal lattice. So the easiest way to take into account the fact that we have additional scattering points. Take into account that I have scattering from other points that are not R. For example, R plus D1. That will give me all the points in this lattice which are not on the Bravais lattice. Let's assume I already fulfilled these points. So I calculated all the points where I'll see interference for the Bravais lattice. Then comes out something, right?
This must equal to 1.
I don't know what it's equal. Just at the Bravais points, I have to take this additional contribution. If I have more than one point, so I take each one of the Bravais lattice reciprocal points which were supposed to give me a contribution to the interference and multiply it by this squared. This is amplitude. And this is known as SK, and it's known as geometrical structure factor. And if I want to know the intensity of this point, yes.
Because I don't question, but the I in the E.
This is I imaginary.
Yeah.
If it bothers you, let's change it to J. I wouldn't change it to K. Have enough K's. Okay, let's see an example. A BCC lattice. We can think of a BCC lattice the way that we defined it. As a Berkovits lattice, all is good and nice. But choosing the description is our prerogative. We can choose any description that we want. So instead of thinking of a BCC lattice, can say it's a simple cubic with an additional, with two atoms. And the second atom, one of them is simply D0 would be at R. D1 will be at A over 2 x plus y plus z. So it's a simple cubic where we have an additional atom in the diagonal of each square. At the middle of the diagonal of each square. That's BCC. As I said, perhaps it's less elegant, but choosing a mathematical description shouldn't change the physics of it. So, what happens to the scattering pattern if instead of treating it as a BCC, we treat it as a simple cubic with two atoms? Shouldn't change. So let's do this this description. SK Okay, so I wrote the first atom, D is just 0, so e to the power of 0 is 1. And the second one is whatever k is, the reciprocal lattice vector times D1.
Why is the 1 there? You didn't say D0 is R?
Therefore, when I'm combining these additional factors, it's just 1.
But why do we need the D0 anyways if...
Because I'm taking the point into account. It's still
so
scattering.
it counts as the D also?
Yeah.
Okay.
Or I could tell you it doesn't count as a D, just add 1 at your convenience. Okay. So to compute SK, I have to know what's the reciprocal lattice vector. Fortunately for simple cubic, we are already able to sing it by heart. Okay, we did it in one of the previous lectures. So now I'm able to calculate SK. I'm writing it in details because once you should see the calculation in detail. Okay, so I multiply here two vectors plus I pi n1 times x1 plus n2 plus n3. Good?
Wait, can you please explain again how we found K?
Simple cubic.
Oh, okay.
Simple cubic is the only reciprocal vector that I can quote off my end because it's just 2 pi over a, same cubic structure.
למה ההבדל בין ה-SK שחשבנו שם ל-SK שחשבנו פה?
But I put on k.
שפשוט הצבתי.
See, that doing it step by step complicates life. Good? Yes. But 0 to the power 2 is still 0. And that's the important conclusion here. Basically, you have lost half of the points that belong to the single cubic. So now, if it's not done in the exercise, I recommend go and calculate the reciprocal vectors of BCC directly. We did it, and see what will be the structure here. And you'll see that you get the same structure. Of course, it doesn't make any difference. Now, my question is, on physical grounds, why do I get less points when I have BCCs than a SC, from a simple cubic? That's my conclusion. Half of the points are wiped out, right?
Because there are more points for the light ahead.
Yes, but why do I lose and I don't get?
Because the particles take the energy? No.
No, there's.
Because the energy is
Save the
conserved.
atom.
Hmm?
Save the atoms. You can put the atoms in the Prof and to break.
Exactly. At the end of the day, we do here a Fourier transform. What do we know about the Fourier transform? It takes structure and projects it on 1 over the length. Here the typical length is smaller. right? Because I have 2 points within my each lattice unit. On a distance that I move in the simple cubic A, here I have 2 points, meaning that my structure will be more spread out, or I wipe out half of the interference points. The more complicated and small scaled is the structure, less Bragg peaks I will see less Bragg peaks. Well, a bit of physical intuition. If I have a disordered sample, by luck, could be that I'll get constructive interference from all these atoms that are thrown randomly all over. But the chance that you'll see it becomes more and more rare. On a typical sample, you'll never see it. Okay. Third question, which we actually have already answered it. Basically, all we have to do is take this mathematics and do some adjustment. We said an atom is not a point. This point has some finite electron density around it. Someone can guess what will we do?
We'll add a ring of D points.
Exactly, not a ring, just a whole smear of D points. And each one will be weighted by the probabilities that I have there an electron belonging to this atom, or by the density of charge of this. So all I have to do and if I have several points to the Bravais lattice, I'll just call it F J, and this guy is just and I could have different atoms, so F could be different for each point here, and I, K. So this is taking into account that I have a Bravais lattice with more than one atom per unit size, and the fact that these atoms are not point-like objects. Okay, now for all these lattices that are mathematical possible in nature, there's very nice group theory, mathematics of group theory that goes into the game, and classification schemes of these lattices. Anyone who's interested can read Ashcroft, I think, chapter 7. I won't go into it in this class, in this course. Okay, so why do we have lattices at all? Now we're going back to the physics. Of lattices. Okay, basically, chemists will insist that you have 4 different classes of lattices of structures. Now the classification is not very sharp, it's a bit fuzzy, but it does give you some feeling about what is happening. Okay, so chemistry in 2 minutes. The whole science of chemistry in 2 minutes. Don't tell our neighbors there that it could be summed up in 2 minutes. They'll have a whole lot of objections to that. Basically, why 2 atoms combine into a molecule?
To fill the electron up?
Exactly. The simplest, and it leaves out a lot of details, but the basic, simplest understanding of why atoms combine into molecules or solids is the fact that they like to have their external electron shell filled. Meaning if they're filled, they don't tend to create chemical connections. Someone knows what these noble gases. Noble gases are happy, again, a euphemism to saying that they are in the lowest energy state when they remain with the same number of electrons that they always had, and they don't tend to create any chemical connections, meaning they don't give or take electrons. So basically, noble gases don't play don't take any part in the game of chemistry. For example, helium, neon, xenon, I think, argon. Do they form lattices?
they're solid states, so I think yes.
Well,
Gases.
they are usually gases, but at very low temperature, and if you add some kind of strong pressure on them, you can create a lattice from them. And then the question is, what is this lattice called, and what is the force that
Hold us together.
holds it together? So these create something that's known as molecular. And what holds them together is the fact that although these atoms are completely neutral, they can create some deformation between the positive nucleus and the negative electron cloud, which creates an
It's a van der Waals force, right?
right, which creates some dipole moment between electric dipole moments, and we know that there is dipole-dipole interactions, and these are the forces. We'll formulate it in a bit, perhaps not in this lecture. So we have dipole and a particular form of them is known as van der Waals forces. We'll define it and see what it means. But it's important to remember these are very weak forces. You wouldn't have them in room temperature, you wouldn't have them even in a few Kelvin. Okay. The second force, the second lattice type is the ionic lattice. They're coming from the first and seventh row in the periodic table. Okay, so the first row is guys like also, and anyone who wants more members, just Google the periodic table and see what appears on the first. And guys from the seventh. Chloride, fluoride, barium, iodine. What is special on the first periodic column?
They have one free electron.
They have only one electron in their outer shell. What is special about the seventh?
They're only missing one.
They're only missing one. Perfect partners. So perhaps the most known couple,
Salt.
salt, table salt. There's a lot of salts. This is the simplest structure. What happens here? This guy gets rid of his electron, says to the chloride, go take it, I don't want to see it anymore. This guy accepts the additional electron, and then you can say, well, it still costs them energy because you separated a positive from a negative charge, so they bunch together. Decrease their distance, so the energies that they gained by transferring the electron from this guy to this guy, they minimize it, although the charges are separated. And then each one of them is an ion. Okay, so if I have two, lovely. What happens when I have a lot of chloride and name escaped me. Sodium. What happens then?
They're organized in a lattice.
They organize in a lattice. A chessboard lattice, or a simple cubic if you well, it's not really, it's let me draw it a moment. So you have plus, minus, plus, minus, minus, plus, minus, plus, and so forth. On the next plane you'll have the opposite. Above a plus will sit a minus, so on and so forth forever. From the atomic point of view it's a simple cubic, but not from a brevet, because above a plus you have a minus. Above a sodium you have a chloride. So it's really a BCC from Brevet's point of view. Okay, so
Can you go over why this is a BCC again?
sorry, it's not a BCC. The easiest way, well, it is
The pluses are like in the middle of all the
of all the minuses and so first, if you want, I'm very bad at drawing, so I won't try to draw it and convince yourself.
So, like a single cell of the lattice
Will be moved. Let's say you decide on a plus and above it a minus is a single cell. Or I'll draw it in two dimensions.
Okay, thank you.
But above it, you have here a plus and a minus, so it will sit.
Yeah.
Okay, why is this and not a triangle? Why isn't it a triangle lattice?
Because
In a triangle lattice, no one will be ever happy. So I'm taking a plus. It says this. So I need here a minus to counteract him. And what do I put here? Plus this guy is not happy, a minus this guy is not happy. So you can't build a triangle. It has to be square. Okay, and these guys are known as ionic lattices. From the point of view of chemistry, they are quite boring. It gave up this additional electron to his body, and it remains so forever. They are just a bunch of ions, each one sits happily in these positions. Now we get to the more complicated structure. Two and six. Basically, twos have two spurless electrons. Six is missing two. Okay, what's the problem? We'll transfer two. Well, double ionization costs much more electrostatic energy than a single ionization. And that is more or less the limit of what can be done. Double ionization is still possible, although it's less stable than the single ionization, and they tend to be usually ionic lattices, but much less stable. Three and five, they have to transfer three. It doesn't work. As a new solution must be found.
Covalent bonds?
Exactly. And for guys in the fourth, it's also covalent bonds. What does it mean, covalent bonds?
The two atoms share their electrons.
No one wants to keep three additional electrons in its own position. So it's all the time like playing with national debt, you're trying to move it somewhere else. So basically, while here I add this picture, this is plus, this is minus, and so on, so forth. Here I have a picture for the covalent bonds. Basically, I have the atoms, and If I'll take a snapshot, where are the electrons? They're basically all the time in process of shuttling to the next atom. And if you take a snapshot of where is the electrical density, where the electrons sit, you'll see them spread out in some directional to the next atom. If you think about it, these are all these chemical models where you stick in bonds in between atoms. All these bonds say that the electron has a preferential density in this direction, and therefore the next atom is stuck at this direction. Metals are in some sense the idealized covalent, where the additional electrons are free to roam everywhere. You don't see even the structure. You see just a complete smear of these electron densities. So electrons are basically free to roam everywhere. Where I stop to call it covalent and start to call it metallic, fuzzy. Now, I want to be very precise because just looking on this simple picture can lead to wrong conclusions. What is the most well-known covalent lattices?
H2O.
Maybe C.
H2O.
C2.
Graphite, maybe.
O2.
C, carbon, silicon, germanium. All of them are semiconductors. So you would think that it has something to do with this covalent structure. No, we will I guess in a month or so, perhaps a bit more, understand why these guys are semiconductors and why these guys are metals. And it's not really connected to the nature of the bonds. It's connected to something else. And once we do quantum mechanics of electrons in a lattice, we'll understand it with no connection to the fact that covalent or metallic lattices. By the way, just for general education, is there really something that's called a semiconductor? No. Semiconductors is a very fuzzy definition. Usually we define the properties of electric transport at zero temperature, and at zero temperature all semiconductors are insulators. So semiconductor has something to do with behavior at room temperature. The definition is actually something that shows decent or semi-decent conductance at room temperature, but these guys will show no electric conductivity at zero temperature. And if we happen to live, I don't know, in 1 Kelvin, we would call them great insulators. So this is just our definition for properties that interest us because we live in an environment that's around 300 Kelvin. That also leads to all kinds of argumets about definition. Is diamond a semiconductor or not, or an insulator? It's on the verge. It gives a very, very, very low conductivity at room temperature. But since you can do all kinds of tricks to make the conductivity a bit better, it's still referred to as a semiconductor. Okay. So, at the moment, we are in a position where we know very well to define what doesn't conduct electricity. These guys. Why?
Because there aren't free electrons in
Aren't free electrons. Electrons very much doesn't like to leave his parent atom and go somewhere else. Neither noble gases nor ionic lattices. Okay, but by the way, why does salt melt in water?
because the water molecules pulls the lattice apart.
But why?
Because the water molecules are polar. So you pull
Right.
the lattice apart.
Water molecules are very special that they have a dipole moment, and therefore they can attune an electric signal in them and reduce the cost of electrostatic energy, meaning that we can separate both atoms and they can live separately at some distance from each other. That's one reason why we are composed of 70% water, because for all the chemistry that we need for life, it's very important to let ions to roam around, not only in a lattice structure. So water is a very interesting molecule. How come it has this dipole moment and enables free ions to roam around? Okay, these guys potentially can be metals, but not necessarily. And when they are or when they are not metals, that, as I said, will be the subject of, once we understand quantum mechanics of electrons and lattices. Okay, but all of this was descriptive. Can we say something more quantitative about these, what lattice structures and what forces work between lattices, and most importantly, what does temperature do to lattices? Meaning, when we have some additional kinetic energy for these atoms, how do they behave? That we'll do in the next lecture. Okay, so this, we started that, you can read about it, chapter 19 in Ashgrove. Sorry, our progress here is not linear. Okay, questions?
Yes. The molecular lattice, is it a structure of the noble gases? They can create, they can form under pressure or low temperature?
Yes.
Okay, and what kind of molecules are these? Is it like each of them for its own?
It's called molecular. It's not necessary for noble gases. They prefer it's single atoms. It's called molecule because in the chemistry jargon, a molecule is something that doesn't want to transfer or accept charge. It's happy.
So what is that called force? Where is the dipole?
The dipole is some small movement of the electron cloud compared to the...
So they are moved because they affect each other all the time?
For this guy, it's a bit preferably to have the electrons a bit up, for this one a bit down.
Okay.